So I'm going to start today's lecture by acknowledging the land on which we gather. This is the traditional territory of the Haudenosaunee and Anishinaabe nations. Their territory was the subject of the dish with one spoon wampum belt covenant, an agreement between the Iroquois Confederacy and the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. We must recognize, like the people of the Haudenosaunee and Anishinaabe nations, that the dish represents a common area of land, and the spoon means that we all have to share this land equally. We are grateful for the opportunity to meet here, and we thank all the generations of Indigenous peoples who have taken care of this land and recognize and deeply appreciate their historic and contemporary connection to this place. While this acknowledgement can be a good start, we do encourage all of you to continue to learn about the land that you live and work and play on, and to take action to decolonize. For example, you can start by visiting the link that we have below, native-land.ca, to learn more about the Wampum Belt Agreement. So with that, I'm going to introduce today's speaker, but before I do so, I'm going to provide a couple of quick announcements. Remember, our Join the Journey adventure is still ongoing. One of the next things we're going to have for Join the Journey is the opportunity to climb the Alpine Tower. It's one of our 10th anniversary events. So over the Join the Journey events, we put together over 20 hands-on STEAM type activities. Every time you complete an activity, you can win a prize, and you have a chance to do the Alpine Tower at McMaster University. Our final lecture will be Learning with Art with the McMaster Museum of Art. The final lecture will happen on May 28th, and we'll have the pleasure of having the education staff from the McMaster Museum of Art join us. This lecture will explore how thinking like an artist can teach us how to look at the world differently and how it can help us design, empathize, and imagine a better future. Okay, so make sure you join us for that, and make sure you keep participating in our Join the Journey events. So with that, I'd like to introduce Samantha Stambula, who works at the Canadian Centre for Electron Microscopy, located at McMaster University. Her research focuses on understanding new car engines that don't use gas or batteries, but work by producing water. And she uses electron microscopy to look at some of the materials that make these engines work. And Samantha is also focused on trying to understand how to make these engines last longer and cost less. She now runs events for adults and kids to get them interested in STEM and learn about electron microscopes and how they can answer so many questions. And with that, I'd like you to give a big warm welcome to Samantha Stambula.
Thank you, Sandy. I like the comment to the watermobile. Yeah, exactly. That's great.
Nice joke in the title.
There is. Who got that joke? Raise your hands.
I sure did. It's a classic.
Did you?
I liked it.
A lot of you got it. Good job. Thank you, everyone, for joining me and for MCYU for inviting me to give this presentation. I've been so excited about it all week. It's really fun for me to connect with you kids to find out what you know and to help maybe teach you a little something new. So today, the presentation, I'm going to make it as interactive as I can. Oh, and I see my little nephew out there in the audience. Hey, Logan. So thank you all for joining. So today I'm going to try to ask you as many questions as I can because I like to know what you as kids already know, and then we can try to make this an even playing field for everybody. So we all have the same information going forward, and so that hopefully you also learn from me. So I'm going to be asking you a lot of questions so I can learn as well. And the other thing I like to point out, and I say this for any presentation I ever give, if you have questions, ask it in the chat or feel free to raise your hand and ask me as soon as that question comes, because I know if I don't ask the question right away, sometimes I forget. And then at the end of the presentation, I'm like, I should have asked Sam that question. Now I'm not going to know the answer. So just ask as soon as it comes up. And that also a lot of the times triggers just more conversation too. So to begin, I'm going to give a little of information about me. So this is me here. I was 9-year-old here, 1998, and I won my first science fair. So what a lot of people actually don't know about me is that I actually didn't know how to read until I was 7 years old. So it took me a long time to learn a pretty basic skill. And it was really discouraging when all your friends knew how to do this, what was basic to them. But to me, it was like, oh my goodness, how are you all doing this? And I have no clue what's going on. So I just want to put that out there. And I like kids to know that even though you're struggling learning sometimes, really, it doesn't mean that you're never going to learn it. It just means you need to find the way that works for you to learn that skill. And as you can see, I did learn how to read. I can read the sign here that says science fair winner. So you just have to keep trying and find that way that lets it work for you. So I think this here with the science fair is sort of what got me first interested in science. I will be honest, even at this point, though, I'd say recess and gym were still my favorite subject. And even into high school, I took gym as often as I could. But that curiosity really at this point, I'd say started and made me want to explore science a little more. So even as a kid, I liked science, but I was still super involved in sports. So this is me here. I did Taekwondo, as we saw in the Kahoot at the beginning. And I actually won some medals, some national medals. And this is me in the local paper. And Taekwondo actually taught me a lot, not just how to defend myself, but there were 5 tenets we had to learn when I was young. And those were courtesy, integrity, perseverance, self-control, and indomitable spirit. So it really taught me that you just always keep trying and try to never give up and just keep that in focus, and eventually things will work out and you will figure out a way of how to get through any situation. And I mean, I really showed that off learning how to read when I was 7. Oh, it says karate and she got a gold. Awesome. Good job. Oh, and it says karate too. Great. Yeah, I really enjoy Taekwondo. Even now as an adult, I still do it. I don't compete anymore because I'm too afraid to get hurt now. But I wasn't as afraid to get hurt when I was a kid. And the other things I used to do was I was a brownie. Oh, your mom. Okay.
When did you get the science fair winner prize?
Like how old were you? Fair, I was 9 years old.
Thank you.
You're welcome. Thanks for asking. And yeah, feel free. Anyone has any questions, just throw your mic on or ask it in the chat. I'm trying to, if you keep seeing me looking over, that's me checking the chat. So then the other things I did too, I also really enjoyed brownies. So this was around the same time when I was 8 and 9. I actually received all my brownie badges. And again, this was just curiosity. Still am very interested in learning new things and new skills, and brownies was a great way for me to do that. It also really got me interested in nature. So that was a little bit about me as a kid, and just always, I was that kid who was always asking questions, which probably drove my parents crazy, but I always wanted to know more. And even now I still like to learn new things. I just started taking ballet lessons as an adult because I don't know how to dance and ballet seems super cool. So it's something new I'm trying.
I also asked too many questions.
That's how you get more information. So before we begin and get further into it, I want to ask you all a question. This is one of my first questions for you. Do you know the difference between an MD and a PhD? And you can ask in the chat or turn on your mic. Yes.
I can tell that MD has an M instead of a PH.
It does. Do you know what those different letters when they're combined stand for? Do you want to turn your mic on?
Yes. D stands for degree, I believe.
Okay.
That's
All
all.
right. That's all you know? Okay, that's good. That's a good start.
So MD stands for master's degree, and then PhD, like professional something degree.
Okay. And I'm seeing actually let me
So ND stands for master's degree, and then PhD, like professional something degree.
okay. And I'm seeing actually let me just check the first, I think.
Yeah, I believe MD stands for master's degree and PhD stands for philosophical degree.
Okay, great guesses, everyone. You are very, very, very close. So MD actually stands for medical doctor, and PhD stands for philosophical doctor. And these are just two kinds of doctors that can exist. There are other ones, but I find these are probably the most common ones, at least that I've come in contact with. So I'm sure you all know of doctors, like when you go to the doctor when you're sick, or if you go to the hospital because you've injured yourself, and those are medical doctors. So they have MDs. So they go to school for a really, really, really long time. And they get to become professionals in the field of medicine. Now, a PhD, the philosophical doctor, this is what I have, and this is where I learned about those water cars, and we're going to talk about them a little bit, is called a philosophical doctor. So get one of these, we do research in a specific area of our interests, and we try to figure out something new or solve a new problem or answer a question that didn't have an answer before. And so we also spend a very, very, very long time in school trying to figure out what that answer is and trying to do that research. So for me, my research was in these. So let's take guesses. I want to get as specific as you can. What is this?
So you are building new technology.
Yep.
Of cars. Something more environmentally friendly cars.
Great guess.
I think it's a blue metallic-y Toyota car.
Okay, blue metallic Toyota car. Good description. What else we have? We have Toyota Corolla, Toyota cars. It's a Prius. Engineering, yes. Electric cars. Okay, we're seeing another Toyota. Great. All of these great guesses. And yes, you're all right. So that's right. I am in engineering. I was in engineering, materials engineering, and that's where I did my research. So yes, you're all right. This is a Toyota. Just happens to be blue. That was the picture I could find. And it is electric, but it doesn't run off batteries. So this little marking here, it says fuel cell. And that's where the electricity comes from. And it's hard to read, but we're going to talk about what fuel cells are.
Charges through electricity.
Correct. Yes.
That's
it
what
does.
Cars use for fuel, electricity.
Right. So if we look more closely at a schematic, so this is an overall schematic of the car. We're going to look at the parts individually.
Mamma mia. What?
It looks pretty complicated. We're going to walk through it. Don't worry. So this is where the air comes in, the oxygen. So we're taking it straight out from the air. So if we look back at the picture of our car, we see it has all these really big grills here and even some vents up here. So this is where the air is going to flow into the front of our car. So the air is going to come in and we're going to direct it into this middle area here. Yep, vents, right. It's partly air powered. Then we have hydrogen as well. So we need hydrogen too. So similar to our gas stations, in this case, we'd be putting in hydrogen. So we're going to put it into this tank and it's going to sit right in here. Next, we need the two of them to combine. So the hydrogen and the oxygen are going to combine in this little area here called our fuel cell. When they combine, which they do all by themselves, they make water. So here's our water and electricity. Does it work better on a windy day? Well, actually, you know what? The car makes the wind by running. And it also would have vents that pull that air in. So I would say it works probably the same on a windy day versus just a regular day.
Sam,
Yep, go ahead.
like, is there any difference between a normal car and this car other than the tank? Like, other than how it's kind of electric powered?
So that's the biggest difference is how we power it. Otherwise, it is the exact same. It has the same exterior, the same interior. It's just how it's powered. So instead of using gas or diesel like you use at the gas stations, we're going to use oxygen and hydrogen. And then that's really cool, isn't it? And then when they combine, they make electricity. So sort of like the cars you're used to seeing now, the Teslas or the Prius that use electricity and batteries to power the engine. This is how we get our energy, is by combining the oxygen and hydrogen. Yes.
So, did you know that water is electricity can pass through it. It's not an insulator, but a conductor.
Correct. Yes, exactly. It is.
What happens with the excess water?
I'm about to get to that. Oh, you're jumping the gun. Just give me a second and I'm going to show you. So after the energy is delivered to the engine, then our car can start moving, just like we have with the Teslas and Prius. So next is, like Gabby's question, what happens to the water? So here's the water. So instead of having, our tailpipes in our cars now, you see a car, if you're sitting behind it, all that gas is coming out of the tailpipe, sometimes right in your face if you're standing near it. Instead of having gas fumes come out, it's going to be water. And more like a water vapor. It's not going to be like a hose that's constantly shooting water out because we don't make that much water, but it'll be just this nice water gas that comes out. And honestly, you won't even see it. You might have some drips at the end. Yep.
So if it was water, then I think it would have been good for watering plants.
It could, if we collected that water, yeah, 100% we could use it to water plants. It might get a little dirty just from driving around, but I think it would still be okay. Yep.
So, do you still have to go to the gas station if you use this type of car?
So it would be a different gas station. Instead of having gas, it would have hydrogen. So yes, but not gasoline, hydrogen in this case. So for my research, what I did was I was actually looking at our fuel cell here. And we were trying to make this material as cheap because it's actually quite expensive. So the cars are more expensive than the regular cars you'd buy today. So we're trying to make it as cheap and as fast as possible. So that's what I was working on then. And that's what I did my PhD on. It took me about 7 years for the research I was doing. And like Sandy mentioned, I was looking very, very, very close at this material. So down looking at the atoms. So to do this, we need a special microscope. So the microscope I used is in this box and it's huge. It has its own room. Oh, what kind of car is it? It's called a Mirai. So it's actually, which means in Japanese, it means future. So it's like the future.
Sam?
Yeah.
Do you know I don't know what it's called, but it's called something of future?
Something future, like the Mirai. I see D saying he's heard of it. So asking how much it cost. I believe when it first came out 3 years ago was $75,000. I believe now it's closer to 60. It's still about the same. Okay. Thanks for asking all these questions. I'm happy to see you all so interested. So this here is the microscope, and we're going to be talking about these microscopes a bit more as we move forward in the presentation. So the microscope is huge. This is me standing with my arms up. I am about 5'6". So this microscope here is probably like 5-ish meters tall. It's really, really big. So this is what I use to study that car. Now, this is what I did for my PhD. So now, as Sandy mentioned, I'm in a different role. So I'm using my knowledge to share it with you as kids and with other researchers to try to get them to understand how these microscopes work and how they can be used. Yes.
I was trying to say the museum of the future, that are probably gonna be in the future.
Yes, exactly. So these are all cars for the future. We're trying to move away from gasoline because, I mean, they emit all the greenhouse gases, and we're trying to save the earth. I mean, I know you've all heard about us trying to save the earth in different ways. So batteries is one way, fuel cells is another alternative to batteries and our classic engines that we have now. So as was mentioned, I have a bunch of puppies. These are my 4 puppies that I've had. This is Rizzo. She's now an autism assistance dog. Gavi decided she wanted to become a pet. This is Kina right here. She was my last dog and is in training right now to help someone who is deaf. And then this is Ziggy, who I have right now with me. So they come to the lab with me and they get used to being out in public and training. Amy, can I have one? You can talk to your parents. Maybe you can start fostering too. So I do this with the Alliance Foundation of Canada Dog Guides.
Yeah, a dog because she doesn't think I'm not responsible. The only pet I had was fish.
Oh, you only have fish? Are you allergic? Is that why? Or your parents won't let you?
My parents won't let me. I'm not allergic to dogs. I've been around dogs before and I haven't been sneezing ever.
You know what? It took me a while to convince my parents when I was a kid to get a dog. And it wasn't really until I moved out and started living on my own that I started doing this. So maybe that's your solution too when you get older. Oh, and it's 2 cats, it's 3 fish and a snail. Oh, that's cool. Okay. So then in my spare time, I also love being in nature. I think we can learn a lot from nature, and we're actually going to explore that a little bit in the presentation. So here's me hiking and doing some climbing and outdoors activities. Okay, so let's hear. I have another question for you all. What are atoms? Tell me what you know about them.
Tiny things in the world.
Tiny things in the world. Good. Okay.
So atoms, they are, these tiny little particles, perhaps one of the tiniest particles in the universe that make up our us, and they make up objects. They even make up plastic and glass and that kind of stuff.
Great. Awesome. Okay. Yep.
I think atoms, basically, they're everywhere. Like, every single thing is made out of atoms. Like, the computer that I'm talking to you people on is made out of atoms.
Yeah, which is kind of crazy, right?
Yeah. The phone that I played Kahoot on, made out of atoms.
Great. Do you have something to add?
Atoms are the smallest units made out of proton, electrons, and neutrons, and they make up everything from dogs, cats, to people.
Great. Very detailed. You know a lot about them.
They're tiny particles, as said, made out of protons, neutrons, and electrons that are able to bond with other atoms to create structures.
Great. You want to add something else? Nope. Okay. And then I'm seeing in the chat here, they are all, I'm assuming, like all around us. They live in bacteria. Knows more about the scientists than the actual atoms. So you're going to learn a lot. Do you want to add something?
Like, this is actually a question.
Okay.
They live with neurons.
They are in neurons. Yes. So neurons in our brain are contain atoms. Actually, our whole body contains atoms. Everything around us contains them. So we're going to explore that a little more. So I know some of you, I am atoms. You sure are. So am I. So we're going to, just to get everybody on the same page, because it seems like we have all varying degrees of knowledge about atoms, which is totally understandable. Everyone's different ages, learning different things in schools. Someone on me without permission.
What is that?
What is what? This video?
The man.
Yeah, the man's a little creepy, but the atom's super cool. So I can show you.
What is that staring at my soul for?
They're gonna teach us about a little bit about atoms so we can move on and start discussing how they make things.
Hello, friends. I am an atom. Yes, an atom. Can you see me? Oh, yes, I
We're
know
not
you can
supposed to
see
see
me
you.
on your screen, but I am just an imaginary picture of an atom. Real atoms are too tiny. You can only see them under a very special microscope. Actually, this big microscope can be called a machine. Okay, now you know that we're so tiny that we can only be seen with machines. Now I have a question for you. Do you know the meaning of your name? Very good if you know it.
Yes.
If you don't know, ask your parents. But I also know the meaning of my name. It means that which can't be cut, that which is uncuttable. Actually, it's a Greek word, which means it is indivisible, which means it can't be divided further or can't be cut further. Let me show you something. Let me ask this man to cut the apple in his hand in half. Now do it again. Please do it again. Keep doing it until you can't cut it any further. Yes, this is the smallest part which you can't cut any further. But it can also be cut under a microscopic machine. So, if you get a part so small which can't be divided further, it is called indivisible. It can't be cut further. It is uncuttable. It is an atom. Let me tell you a secret. Everything is made up of atoms. You, this water, this table, this blackboard, this fan, these fruits,
That's not water.
everything is made up of atoms. Oh, you're right too. Everything is made of molecules, but all molecules are made of atoms. Confused? Go to the blackboard and write any sentence. Good. Now this is a whole sentence. Now circle all of the words in this sentence. Now let's take a word and circle all the letters of R with some other color. Very good. You see, this sentence is made up of words, but words are made up of letters. So letters are the smallest units of a sentence. Similarly, everything is made up of molecules, but molecules are made up of atoms. So atoms are the smallest unit of everything. Look at this. See, water is made up of water molecules, but water is made of atoms. There are 2 atoms of hydrogen and 1 atom of oxygen in each water molecule. So when atoms join together, they form a molecule. And when molecules join together, they form a thing. So now you understand. Good. So now, friends, now I would show my body. Yes, I would show different parts of my body. In the center of an atom, there is the nucleus. It is made up of even smaller parts. These are called protons and neutrons. Each of these protons carries a positive electrical charge. The neutrons are equally as heavy as protons, but don't carry any electrical charge. So, the nucleus of an atom is positively charged due to protons. Now, electrons are outside the nucleus. They are orbiting around the nucleus. The electrons carry a negative charge. The total negative charge of electrons is equal to the positive charge of the nucleus. So in total, an atom is neutral. The positive charge of the protons is neutralized by the negative charge of the electrons. So it is like +1 is neutralized by -1, and overall charge of an atom becomes 0. The electrons are moving outside the nucleus at a very high speed. Can they run away from the nucleus? No, they can't run away. Every atom has the same number of protons, electrons, and neutrons. So there is an attraction between equally strong negative and positive charges. Due to this attraction, electrons can't run away, as positively charged protons keep them pulled towards them. Hope this is all clear to all of you. Otherwise,
Okay, I hope
you can always
that's
go
all
back.
clear to you too. I'm seeing that there are a bunch of questions in here, and it looks like a lot of them got answered from the video. But I'm seeing one asking, what are protons, neutrons, and electrons made out of? And it was saying they're made of quarks. And that's right. And you're mentioning the up quark and down quark. There's actually 6 different quarks, and they're called flavors. And I don't remember what all of the flavors are. After that, there's subatomic particles. If you ask me what makes those, that's as far as my knowledge goes. You have to talk to a real physicist at that point. Good questions. I think we need a physicist on this to help you out. You have a question?
What are neutrons made of?
So the protons, electrons, and neutrons are all made of these quarks, and there's 6 different ones, and they combined in different ways to make the the electrons, protons, and neutrons. I don't remember what exactly the different mixes are. Our atoms quirky. Nice. That's pretty funny. Nice one. Good job. So I'm going to ask another question and then we have another video. How big are atoms? Small. Yes, very small. What else? What does everyone else think? Do you know how small?
They're small boys.
Yeah. How small? How small?
Very
Microscopic.
Yep. So we know a meter is about this big. We know from COVID, we're supposed to stand 2 meters apart. So I wrote it down for myself so I'd remember how many zeros to tell you. An atom is about 0.00000000001 meter. What does that even look like? So that's what this video is going to help show. How many zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros.
9 zeros.
And then a 1. So tiny. Yes.
9
So
zeros equals
right?
1 billion.
Divide 1 meter by 1 billion. That is how big an atom is. You need scientific notation. Yep. So it's 10 to the minus 10. So let's watch this video. It's going to give us a better idea. We're going to keep zooming in. So now we're looking at this lady here. These are all things we can see right now with our eyes. We're starting to really push it though.
Ew.
Here's a hair. It's 100 micrometers, which is 10 to the minus 3. In the hair, we have the cells. And those can get divided down to these bigger things called macrofibrils. And if we look even closer, we have these microfibrils. And if we keep going, we have these protofibrils. I'm going to go one more step closer. And we have these things called keratin. That's what make up the hair. If we look closer in the keratin, we can see it's made of 4 atoms: carbon, oxygen, nitrogen, and sulfur. And we can get even closer, and that's when we see the atom. So in this case, we're looking at the carbon atom, it's called 67 picometers. So picometer is 10 times to the minus 12 of a meter. So yes, very, very, very small, giving the screamy face. Yeah, exactly. And that's why we need those special microscopes to look at them. So we know how small they are. We know what atoms are. Now, my question to you is, how many are there? Let's see some guesses in the chat or just shout them out. How many different types of atom exist? We saw 4 in the last video. Yep.
I think 92.
92, good guess.
I think there's like 118 atoms in the periodic table.
Hey, 118. I'm seeing it says 1,000, just a wild guess. Good guess. You can see on the periodic table 118. Okay, let's move on. It looks like you guys.
1 billion.
1 billion, Ronnie. So many atoms. 109. All right. Jasmine's giving you the link that we're going to just explore quickly. So this is called the periodic table of elements. So an element is a material that is composed of only one type of atom. So it's, for example, this is carbon. It would be just a chunk of material that only has carbon atoms in it. So there are in here 118 atoms. Of these, 92 occur naturally in nature. They just happen. We have 20 that are man-made. So there's physicists out there who use these massive accelerators and they make the atoms go at each other really fast and they collide, and then those can make new elements for less than a second. So that would be these elements here and then these ones here. So those don't occur naturally and those were man-made. Yeah, kaboom, a big kaboom. but the rest occur naturally. So let's check out, I'm going to share a different screen. We'll check out some of the different atoms. And then you have this as well. And then you can look at it too on your own time. So let me just pull my chat back up. So for example, helium, this is number 2 right here. Helium, which maybe some of you know is in balloons. It makes our voices really high and squeaky if you inhale it. And each atom you'll see has a name. So in this case, it has helium, it has a little symbol, and it has a number. So this number is telling us how many protons exist in this atom. And each atom, it's unique. So just like each one of us are unique, we're all different, each atom is unique. So it has its own number of protons and its own name. And that's how they're arranged on this table here, our periodic table of elements, based on the number of protons that it has. So you can go through and click on the different elements. So example, here's one called sodium, and that's used in our table salt. So the salt that we would put on our food. So you're more than welcome to look at this a little later and explore what different elements exist in our daily lives. Okay. Yes, do you have a question or a comment?
We use oxygen in our daily life.
You're 100% correct. Without oxygen, we would not be able to live. We'd have nothing to breathe. So oxygen is very key to human survival. So my next question for you, how do atoms make everything? What are your thoughts? Yes.
Maybe they bundle together somehow to make certain consistencies or something like that. I don't know for sure.
I was learning about atoms, and it said that 92 were naturally found in the universe, and then 26 were made artificially because there's like new ones or something.
Interesting. Yes. So that's possible. Maybe I have an old periodic table.
Okay, I just wanted to make sure because I was like,
yeah, so scientists there's a few of the accelerators. There's a big one out in Switzerland, and that's where they're doing all these.
The U elements that I haven't really learned about, well, the ones with U at the beginning and like the 3-letter ones.
Yes. Yeah, they start to run out of just little simple acronyms. They have to add extra letters now.
I think that when atoms combine, when they make things, I think it just happened that they just happened to come together for some interesting reason, like for some way, like maybe water might come somewhere where there was this certain place.
Yeah, just like my car engine that I was showing at the beginning, right?
Yeah.
Did you want to add something?
I think like the atoms turn to like molecules, and they make molecular or covalent bonds depending on what they're trying to make.
Wow, you are pulling out some big important terms there. Nice. So we're going to talk about those actually. And I'm seeing Jimmy's interested in the watermobile. Honestly, I love that you are calling it the watermobile, and I'm going to start calling it that now. Okay. So we touched on a lot of different things, and you guys have so many interesting ideas, and they're all right. So we're going to start discussing that. If we have an oxygen atom and 2 hydrogen atoms, who knows what this is? Shout it out. Water, right? Water, classic watermobile.
H2O.
Water, yes. H2O. Yes, water. So water is made up of oxygen and 2 hydrogens. And that's called a molecule. There's lots of different molecules. We're going to use water just because it's one that everybody knows. It's all around us. So if we have just water, H2O mobile. I mean, that's good. So if we have just water, we typically know water is a liquid. So when we have water, we have all these little molecules floating around, and they interact with each other. They have little imaginary bonds, not imaginary, little invisible bonds that we can't see. So in water, these little molecules are moving around. They're not super rigid. They can move a bit. And that's why they take the shape of our container. Now, if we heat that water up, so let's say it's outside and there's the sun, or we're boiling it on our stove, it's going to create gas. So that's water vapor. What happens there? You'll notice now we only have these 5 molecules that I could fit in the screen, whereas for the liquid, we had a lot more. So with the gas, we're giving these molecules tons of energy. So they're going all over the place, going super fast and really crazy. They're further apart. And that's why this gas expands, because we provided these molecules with all this energy that they can move. So that's another thing we can make with water. What if we make it really cold? So now the water is going to become a solid, and that's ice. So now look at how many molecules we have packed so close together. So when it gets really cold, the molecules aren't going to want to move. They're going to get really close to each other and make these solids. So we can see, yes, do you want to say something?
In winter, will a watermobile freeze?
Good question. So we do have part of the system would have it heated up, so it would stop it from freezing. But very good question. Yes, that's something they had to think about before being able to actually design it. And now Alexis is saying one more main step, and we could have went through the whole water cycle. Correct. Precipitation, evaporation, condensation. Exactly. So we see this happening throughout our days when it's raining, or even on sunny days, we're collecting our gas vapors. And then if we think about it in the winter, we have snow and ice forming. So with this only one molecule, which has 2 atoms in this case, we've created 3 different things. And this is just one example. So my next question for you then is, so that's one example. What are different ways that we could form materials? So we saw that we could heat them up or cool them down, and we're going to create these 3 different things. What's something else we could do? Yes.
If you combine it like other molecules from like different things, you can make different like substances in like a lab, because sometimes not necessarily safe, but makes material.
Yeah, awesome. Yeah, of course. Saying heat, cool. Yes, heating and cooling. Any other suggestions? What else might I be able to do to make different materials? I mean, we have all these materials around us. What else is happening? I got you stumped. Think about it. A laser. Interesting. Yeah, that's definitely one way. Do you want to answer? Okay, let's look. So these are just a couple of more examples. Do you want to try to say something?
Fire could change things.
100% fire can, yes. Do you want to try?
So we could, add in more molecules to make, a new substance, like they did in those labs to make new substances in the periodic table.
Right, nice. Good answer. What would you like to add?
Nuclear fusion.
Nuclear fusion, definitely. So everything you guys are suggesting are these chemical changes. So we can change things by changing the chemistry of the material. And there's lots of different ways that we can change things. And I think it was mentioned this. She said adding, and mentioned this as well, adding different molecules. So yes, so we can change the molecules that combine. We can also just even change how the atoms themselves are arranged. So if we remember, I mentioned carbon. Both of these things, diamond and your pencil lead, which is called graphite, are made of carbon atoms only. So they are essentially the same material. They're both carbon, but by changing how the atoms are arranged, you create 2 very different materials. Diamond, we know, is these really shiny, pretty minerals, and you see them a lot in rings. They're very hard, whereas graphite or our pencil lead lets us write. Yeah, diamonds and pencils, exactly. They are the same material, both only carbon, but the atoms are arranged differently to create 2 very different properties. I see some hands are up. Anyone want to add something? No? Okay. Another way is we can mix atoms together. So whether that's mixing different atoms to create different molecules or mixing them in something that's like a metal, which would be called an alloy. So if we do this, I have an example here, actually. I'm going to try to get it up to my camera so you can see. This here is gold. You can see this gold earring. It's made, we're going to say it's made all of gold. It's not really, I don't have that much money, but let's for just the sake of this example, this is pure gold. It's yellow and it's in my earring. Now I have this example here, which is also gold, but it's white. So let's see the two of them together. So one is yellow and this one here is white, and that's called white gold. So for the white gold, what they've done is they've actually added zinc, nickel, and copper to it, which gives it that white color. It also makes it a lot harder. So if you wanted a stronger earring or a stronger material made of gold, you would use that instead. So you can see that just by simply changing how the atoms are arranged or by adding different atoms to the element, we can completely change our properties. So we could make something harder or softer or really flexible or more rigid or maybe even transparent so we can look through it. So we can do all these different tricks to make all the different materials that we see around us. So my next question for you is, can we see atoms? No, no. Okay. So I'm seeing a lot of no's. Yes. Would you like to turn your mic on? Under a microscope, yes, unless you are a scientist.
You can only see it with a special microscope.
Right. Did you want to add something?
It was just the same thing the other person
Same
said.
thing. Okay, correct. So you're all right. So we can't see them with our eyes, but we can see them with a special microscope. So I'm going to show you what they actually look like, but I'm going to quickly go through how we look at materials and describe materials. So this little thing here is called a gecko. I don't know if any of you know geckos. They're really cool. They have these sticky feet and they can stick to glass and all different materials. So I like to say our eyes are a first line to look and examine materials. Like if I have this pen here, I can say, okay, the pen is white, it's hard, it has black spots on it. So we can use our eyes first to describe a material, but that's only going to get us so far. We can't see infinitely with our eyes. So next, maybe some of you have used one of these, a light microscope. So we can see this little boy looking down at this material. And this is what the gecko's foot looks like under a light microscope. So we can see it has, which we can't see with our eyes, all these ridges on its pad of its foot. But this doesn't let us know why it's sticking to glass. I mean, we can't walk on glass. At least, I mean, if it's on the floor, we can, but if it's on our windows, we can't walk on it. But why can the gecko? So this means we have to look even closer now. So I've got a microscope for a few years. Nice. Yes, microscopes are a lot of fun to play with. So there's these microscopes called electron microscopes. So if you remember our atom, it has electrons that spin around it. So we can actually use those to look at materials instead of light. So the electrons are going to come down and they're going to hit our material and we're going to be able to see these pictures. So if we look now really close at these little pads, we can see it has these tubes with little packets. And if we look even closer, we can see within those packets all these little hairs. So you can imagine each one of those little hairs is acting like a suction cup. So one of these pads here of the foot has billions of little suction cups, which allow the gecko to actually attach to things. And that's how they're able to do it. But without these special microscopes, we don't know about these fine features in the microscopic world. So we can use these to actually look at atoms. So this is that microscope I was looking at, and all these little white spots that we're seeing here moving around, those are all little single atoms of gold that are moving around on our sample. And that's what atoms look like. All these little white spots here, those are atoms. Could you make shoes out of the same technology? Very interesting question. for people to do that, it would be very difficult because we do weigh a lot more than the geckos, but they are using those geckos' paws to make specific, to try to engineer materials that look the same so that we could try to get those properties if we want. And that nature does teach us a lot of things like that. We try to copy nature to make materials that we can use. I see 3 hands up. Do you have something to add, or is that from before?
I was just gonna say that's one of the main reasons why scientists are trying so hard to stop like extinct species, because we need to learn from them, because they were here before us. And you look at the geological eras, they were there before us, right? So it's like, they've been adapted in ways that we haven't been able to discover or aren't biologically possible for us.
Very good point. Did you want to add something?
We could make new technology from these gecko thingies, the gecko pads.
Yeah.
Like grip onto walls and stuff. We could even be the next Spider-Man.
Did you want to add something?
I just had a question. Why are atoms white?
So that's just how they appear in the microscope. So the way our detector works is it just detects whether an electron actually sees something. So what it sees is the atom. So all our images are in black and white, but I can add color if I want to. Great. Good questions, everyone. And yeah, exactly. Like we're saying, like adding here with the gecko tape and Gecko Man. Yeah. So we need to learn a lot from biology, and we need to learn a lot from these animals because they've evolved over tons of years, and we can learn a lot about how to engineer materials like that. You can dye the atoms with a special dye. I can color the atoms using the computer. There are dyes for cells, and those are cells in our body, and we can use them to help us look at those under the microscope as well. So I want to play a quick game with you. This is going to lead us, what color are atoms? That's a very interesting question. So atoms, which I didn't get into, are these really kind of weird things. And you might learn about this later as you get older. So atoms actually can be described as a wave or a particle like a ball, depending on how they're behaving at that time. So the color that I would describe an atom will depend on how fast it's moving. And that is what would produce potentially a color. For namesake in the microscopes, they always just appear white because that's how our detectors work. But is there a red atom? If it was moving at that speed, then yes, almost like particle theory. Exactly. You nailed it right on the head. We are getting into particle theory here. I mean, we can speed up atoms, we can slow them down, and that's what's going to potentially give it a color. Inherently, I would say atoms, if an atom is just sitting there, it would have to do something special to have a color. And we're not going to get into that too much because that's really pushing the limits of physics here and quantum mechanics. But wow, you guys have a ton of great questions. Did you want to add something?
Are there blue and green atoms?
If they were moving at the energy that would produce blue and green, then there could be, yes. I know that's a very abstract answer, but atoms are very abstract things to understand. So I'm going to play a game with you. So I'm going to show you some pictures that I've taken, and I want you just to quickly guess, put it in the chat what those things are, and then I'm going to show you. So what does this look like to you? What is your guess? Velcro. What else? You can just say it quickly over your mic too, if that's easy. A cactus. Another cactus, a shirt, a hairy thing. Nice. Good guesses, everyone. Another Velcro.
It reminds me when they zoom in on plants to talk about like what's called the chlorophylls.
Interesting,
like
Alexis.
Color. Yes. That's what it reminds me of. That's why I said cactus. And like,
yes. All right. I'm seeing dog, fish, cat. So many things. Okay. So this is actually the wing from a wasp. So if we zoom in really, really, really close to the wasp, this is what the wing looks like. And it actually has all these little spikes and hair on it. So these actually spikes here help the wasp to defend itself. So if something rubs against its wing, it can trigger its leg to kick, or some of these receptors can actually be used to help it find pollen. And it helps stabilize it when it's flying. Isn't that the sword or stinger? No, these spikes are actually on the wing. So yeah, sort of like nerves. So yeah, it helps it with protection. It helps it fly straight and not fall over. So by looking down at this microscopic scale, we can start to see these spikes, which we had no clue were there before. All right, what's this? Rose. What else? What other guesses? A flower. What do you think?
Rose.
Rose. Okay.
Blood cells.
Blood cells. Interesting.
I was about to say that.
Amy was going to say that too. Kai thinks it's red blood cells. We have another Rose.
It
Okay.
reminds me of when they like bugs and red
Cell.
Are they crayon shavings?
It's cell or even your vein.
Ooh, a shell, a rock, a gem. Interesting. Good guesses, everyone. So this
house.
Oh, sorry. This is actually part of a battery. So these special batteries here, they're called sodium ion. So sodium comes from salt. So these are inside these special salt batteries. And this is what helps. This is where the salt is going to move back and forth to create the power. So the salt batteries are very similar to the lithium ion batteries, but instead we use salt because there's a lot more of it in the world. Oh, someone said it looks like a liquid. Thought it was a salt crystal. Oh, you thought it was a salt crystal. Awesome. Oh, just learned about that. Good job, guys. All right, another one. What's this?
That's a beehive.
A beehive. Nice, Ronnie. Gabby, what do you think?
A pigeon. A pigeon's feathers.
Oh, nice. Interesting guess. A fly eye, an insect eye, memory foam. Cool. Bee's nest, beehive. Parts of a cell. Good guesses, everyone. And actually, some of you were very close or right. It is the eye of an insect. So these are actually called compound eyes. So each one of these little hexagons acts like a little microscopic lens, and then the ant's brain is able to combine all those images together to get this huge vision of the world around us. But then you also see it has these little spikes on the eye. So these spikes are sort of like eyelashes, and they stop these big particles from landing on the ant's face because it doesn't have hands like us that could easily wipe them away. So one last one. Actually, there's one more after this, but what's this?
What is that?
A carpet. Yes,
Your
Gabby.
vein. Rags.
Rags, trash, cloth fiber.
It might be your vein.
Okay. A ring. Yes. All right. Great guesses, everybody. So this is part of a t-shirt. So in the t-shirt, we have this braided structure, which is then formed by all these little cotton fibers, even smaller, to make it nice and strong. Yeah, you were so close. So yeah, this is how our clothes stay together, is by adding these layers and layers of these strings all bound really tight together. Exactly, fibers, cotton fibers. So I have one last one, which is going to be a bit of a video. So what is your guess for this? What does this look like?
A little house.
A little house.
Gingerbread on a cake.
Gingerbread house on a cake. Oh, nice. Gabby, what do you think?
World's smallest house.
World's smallest house. All right. Gingerbread house, 3D printed house. Okay, a lot of houses. So let's watch the video. So you're all right. It is a gingerbread house, and you were very specific and actually right. It is the world's smallest gingerbread house. So we made this at the lab. We're going to show you how we made it. So we started with an element called silicon, and we cut out different walls. So this is us making the walls. We have this little needle that can come in. We're going to take the walls out and start building our house. So there's the front, the back. We're going to put the roof on. And then we're going to use, there's our little chimney. We're going to use these gallium atoms, they're called, and we're going to be able to write these different things in it and make our decorations. And here's our gingerbread house in 3D. It's very small. Has anyone eaten it? I hope not, Owen. Just give it a sec. You'll see why. So this little house is actually sitting on top of a snowman. Just wait. Here is a human hair. So this is our little itty bitty house that we saw in the last picture on top of this little itty bitty snowman, all smaller than our hair. So we can actually use these microscopes not only to look at things, but build things as well down on the microscopic scale. It would be very filling. You guys are so funny. Oh my goodness. So that's what we can do with these really fun instruments. So we can make the world's smallest gingerbread house.
You guys should 3D print that gingerbread house for like display purposes. Like, and you could do it like a museum or something and have like a display 3D printed version of it.
Actually, that's a really good idea. I like that. I'm going to bring that up with our next group meeting.
You know, also like, and they have like the little screens and then it says like a little history. Like,
yeah, exactly. So this is going to be my last slide and it's going to be our wrap up, and we can maybe just use a little bit of time to discuss it, but it's going to be more for you kind of to think about, to go what you're going to think about from this lecture. So why do we want to look at materials at such close details? And if anyone has some answers right now, maybe just say it quickly on the mic or put it in the chat.
Knowledge.
Knowledge, yes. Yes, we gain a lot of knowledge by looking down at these scales. Scientific discoveries, exactly. What else? Right. So those are great. And I'm going to let you think about that a bit more. And I'm going to maybe give you a little bit of information to think about. So we like to be able to look down at these such small details because we can see how things are made. Advanced human knowledge, advancement in life as we know it exactly. So if we can understand how these atoms are combining and how different things in the world are happening, exactly how things work, we, as everyone was saying, we gain knowledge, we gain scientific discoveries, but we can also start building things. So if we understand how other things work, we can start using that in our everyday lives to start engineering things as scientists and making new materials and new things that other generations can use. So industrial revolution, exactly how things work. Yeah, that's exactly why we need to start understanding things on this level. So with that, I'm gonna let you all kind of ponder that a little bit more in the rest of your day. And I'm just gonna thank you for attending and listening, being so attentive and asking so many questions in this presentation.
Thanks so much, Sam. That was an amazing lecture, and I love the number of questions you got and all the ideas that our audience raised. So I think we've had a lot of discussion. Sam left you with some very interesting questions to think about. If you want to keep contributing, you can just email them to our MCYU email address and we'll forward everything to Sam. And let's get Jasmine. You have a bit of an announcement at the end, I think.
Yeah, I just have a quick announcement. So as Dr. Raha mentioned at the beginning of the lecture, this is our 10th anniversary, and we put together a ton of activities for you guys to do so you can win prizes and do the Alpine Tower at McMaster University. And so today's lecture actually counts as an activity. I also put the link in the chat, or you can type this in to Google and you can log your participation for today and have a chance to win.
Great. Thanks very much, Jasmine. With that, I want to really thank Sam Stambula for her wonderful lecture. I think you all know the answer to her question now in terms of what was the joke again? I forgot actually.
Why can't you trust atoms?
That's right. Why can't you trust atoms? So there's one for all of you to try out on your friends. So remember to join us for next month's lecture. It'll be the last lecture for this year. We'll have some exciting announcements to make there. And thank you all for joining us. And thanks for sticking around for a bit longer too. Have a great month, everyone.
I have a
Take care.
question.
Sorry. You have a question. Didn't see your hand.
Oh, Yeah, so like there have been like a few movies where like they shrink stuff to like atomic levels, and I recently saw something called like implosion fabrication that was like founded by MIT that like shrinks things, that can build things and then like shrink them really, really small. So like I'm wondering if something like that can happen, or is human technology not advanced enough?
That's a very interesting question. And to be honest, I don't know the answer to that. And I think that would take a little bit more exploring on and research on my part. If it came from MIT, honestly, it might be something that's happening. Those scientists out there really are on the cusps of everything new in knowledge. So maybe I don't have much comment. And honestly, that's a bit about science, is being able to admit when you don't know something and saying you will look into it.
Yeah, that's a really good question, Kai. If you saw it, maybe you can share it with the MCYU email, because I'm very curious. I don't know much about that too, that if we can really shrink things like that. Did you have a question also?
Okay, this is completely hypothetical as pertaining to the previous question, but if they had the technology to shrink a said object to like molecular and like atomic levels, could they possibly make the technology to reverse that so that you could like explore the atom in like a bigger version? Like, not like, I'm not saying massive, but you know, it's like bigger than it is.
Again, a great hypothetical question, and I don't know the answer if it's possible. I do know that if it was possible, that could lead to some very, very interesting discoveries that would make things a lot easier for us to understand things if we could make them big enough that we could use our eyes to actually start examining these very small materials. Maybe we could even answer questions about what makes up quarks, and then what makes up those, and what makes up those. We could just start making things bigger to understand them.
Yeah, that's I'm just thinking about that. You know, if you made something small, I would hope you could make it big again, or the other way around, or you'd be in a lot of trouble.
Kind of like the movie Honey, I Shrunk the Kids.
That's exactly what I was thinking of. Do you have a question?
What about those, cutting devices under like, those special microscopes that Stan talked about?
Yeah, so we can build things under the microscope, and actually there's other microscopes, they're called scanning tunneling microscopes, where you can actually move single atoms. So you can take an atom and move it along the surface, and you could build things that way as well. So that's how you could build something on such a small scale. And that, I would say, is the first step to start being able to do that. I'm still very curious about this shrinking things down to the atomic scale, though.
Did you have another question?
So what time is it?
It's 12:20.
If you could grow things, I know that if you grew a blueberry to the size of a football field, then the atoms would be the size of a marble.
Yeah, so the nucleus, where the protons and neutrons sit in that scenario, are the size of a marble. So the atom itself, it is quite large just by the volume that the electrons take up. But then in the atom itself, there's just a lot of nothingness. And then at the nucleus is actually where all the mass sits. So the protons and neutrons contain all of that mass, and then these electrons spin around it, taking up all that extra space.
Yeah, it says there's a TED Talk video about this. So maybe you all could have a look at that. So thanks again, everyone, and thank you, Sam. This is an amazing discussion. I love all the questions that are coming. But it is getting a bit late, so we'll thank Sam again and say bye to everyone, and look forward to seeing everybody next month. Take care of everyone. Bye.
Thank you all. Bye.